Okay, hello everyone. So Salman is going to tell us about categorical quantum mechanics. I think that's all. Yes, please take away.
Thanks, Cihan. Also, thanks for handling the Zoom and the recordings. So a few weeks ago, I gave a talk that was going to be motivating this very talk. So luckily, we had Walker ready, and then Walker again explained some basic structures in category theory, symmetric monoidal categories, dagger categories, and associated sort of results. And now our sort of goal here is to see, we want to interpret the structures of dagger compact closed categories for quantum protocols or even quantum mechanics more broadly. So that's our basic idea. And so just in case you guys perhaps did not remember, let's just recall a couple of things from the last talk. So we have that a dagger structure on a category C is in well, how do I spell this? Okay, yes. Dagger C to C, that is identity on objects. I will use a dagger cat. Yes, sorry, wow. I wrote it wrong in my notes. Yes, I think that that's probably where the confusion comes from, but yeah, C-op is more correct here. Thank you. As a category, a dagger category is a category equipped with dagger. And just, I want to remind you guys of a couple of things because we'll be using these identities very ubiquitously, I guess. So this dagger satisfies one. We have that GF composition dagger equals F dagger composition G dagger. This is as we would expect from F Hilb. We have that the identity dagger and also we have the involution that dagger equals F. So the following ideas or the following notions can be given a precise definition in a dagger category. So we have a morphism F from A to B in a dagger category. So we have we can talk about the adjoint. So F, so the way that I'm structuring the statement is F is the adjoint of B A G when G dagger, or F, sorry, F equals G dagger. Hopefully that kind of makes sense. So it's self-adjoint. If we have F dagger equals F, and in this case we have A equals B, it's idempotent if F equals F. Again, here we have equals B. We have that it's a projection. So basically what I'm doing here is just saying that many of the things that we find to be natural in F-Hilb can be defined more generally in a dagger category. So we have that a projection is self-adjoint and idempotent. And we also have the notion of a unitary, which is F dagger F equals identity on A, where F dagger equals identity on B. And also, it's positive if F equals G dagger G for some G A to B and A equals B. Okay, so that's just, we wanted to make sure, okay, here's that stuff. We want to make sure that we can talk about all of these things, because then we will later use them for developing our quantum protocols. So just to remind you guys from a couple of talks ago, we have some terminology here. We say that a map psi from the unit to some object A is a state, whereas we can talk about this as being some, they use the word co-state, or you can say it's an effect. And so we can also talk about the inner, so this would be in, I did it maybe. It's a dagger? I mean, it doesn't have to be the same.
Okay, so
It's just a,
is the dagger.
okay. Yes. Yeah, I should say that. Exactly, yes. Okay. So maybe it will be easier to, yeah.
Now C is a symmetric node. Right?
What's that?
Now C is a symmetric node.
Yes. And so, for instance, the inner product can be defined like as follows. So you have something like, for some then you can talk about something like dagger psi is a map from I to I. And in fact, we can see that this definition of unitary will preserve this notion of inner product. So if we have something like, I'll just do it like this. Okay, this is the same phi. Dagger u psi. Then this is going to be using our properties. Phi dagger, u, and u is a unitary. This is equal to identity, so we have that this is phi dagger psi. A couple of other things just for the terminology. Sometimes we'll talk about, I believe it was Walker that introduced the name of a, should I remind you guys what the name of a morphism is? Okay, so let's do this. So we have that a name will be something like this. So if you have some morphism A to B, then A dual tensor A, then it will probably be something like this. Identity on this tensored with F A tensor B, and we define F to be this. And so we can interpret this kind of map from the identity to this kind of object as a preparation of a certain kind. This is a certain kind of quantum state. They say that this is, they interpret this as, so this can be interpreted as the preparation of a Bell state or an entangled state. So for F A to B, Bell. Okay. Okay, so okay. So let's just continue with that sort of section over there on the terminology. So we also want to say that if we have some psi like this, then we can define the notion of a projector. So we have a psi like this, such that psi dagger psi equals identity on A, then define some psi dagger, which is a map from A. It's not the opposite of pure. Yeah, you can. There's mixed, and then there's unentangled and entangled. There's pure, and there's mixed. So if just, I want to remind Reddy for a second. So if I have, I'm just going to go to the land of Hilbert spaces for a second. So if I have a Hilbert space HA and HB with bases E, A, I, and E, J, B, respectively, then I can expand any vector in, so if I have some psi in HA tensor HB, in fact, I don't necessarily need to introduce the notion of basis here. All I need to say is that it's unentangled, psi is unentangled if it can be written, if psi, maybe, I'm messing around with the notations, sorry. This was that Dirac notation. If you can write psi as being equal to some phi A tensor chi B, then it's unentangled. Otherwise, there exists some psi A and chi B such that if it has this sort of product form, then it's unentangled. Yes, exactly.
Otherwise, it's like
Yes.
it is not optiparodic, right? For like local operation, classical communication.
How do you mean? It's unentangled if it satisfies this for some states.
For product state.
Yeah, that's what I'm.
For all states.
Oh,
that does not
you're talking
satisfy
about
this.
quantum. You're talking about density matrices.
Yes.
With density matrices, if you have a convex sum of product states like this, then you might call that one unentangled as well. But I believe for pure states, this is the only definition. So this thing is actually a projection, and you can sort of think of this as projecting onto, I mean, in the Hilbert space notation, we think of something like this as projecting onto the one-dimensional subspace given by psi, which is a vector. So you can actually prove, not so hard, that psi dagger is equal to psi. I mean, that's pretty apparent. And then also just that this is idempotent is also straightforward to see. So in fact, this is a projection. Okay, so I just also wanted to, last time Walker talked about byproducts. So the way that byproducts are going to show up in categorical quantum mechanics is that typically we're going to think of certain observational branches as channels as being, so if I can take, for example, going a little bit off script, but if I have, for example, some unitary, perhaps U, just to give you guys an overview, that maps from A to I equals 1 to N of where this is some unitary. This is perhaps like a spectral decomposition or something like this. When these are perhaps the unit object, I can think of this as decomposing A, which is like a Hilbert space, into a direct sum of its one-dimensional subspaces. I mean, this is more general what I wrote down. But, and then you can think of each of those as being the outcome of a measurement or projecting to a particular one-dimensional subspace. So the byproducts, and then you can define functions, stuff like, 1 to n of fi, and what do these do? These do precisely what you would want them to do. That is, they act the morphism fi on the appropriate part of the direct sum. So after you do a measurement, you're going to have these different observational branches, and you're going to perhaps apply a different morphism or a different unitary to correct for the different measurement outcomes. So you want morphisms that act like this. Yes. So do we remember byproducts? Is this okay? Should I define them again, or you guys are okay? Okay, yes. You guys are probably better than me. So the one thing that I do want to remind you guys from, which is going to be very nice and useful for us, is that byproducts distribute across the monoidal product. Maybe I put this in some quotes because this is just my intuitive understanding. And in particular, we have these natural isomorphisms which do stuff like this. So A tensor B plus C, A tensor B plus A tensor C. So this is for distributing from the left to the right, and we have V, A, B, C as doing just the opposite. So if I have A plus B tensor C, this is exactly what you would hope for. A tensor C plus and so this is, there's an interpretation that goes with this as well. And it will become more clear as we work through some of the examples. But for example, if I split my Hilbert space, I do some observation and I get one branch and a second branch. And this is another party, or another qubit tensoring with C. C does not see these different observational branches until I apply this functor, and I actually have that the particular outcome associated with this branch is now, so now C is actually a part of this branch intuitively. Yeah. Yeah. Yes. Yeah. So once you apply this functor, you actually have that C can sort of, in some sense, access whatever the outcome is here. That's how you would interpret that. Okay, so more to the point, let's talk about measurements. So a lot of these things we've already talked about, but just we haven't put the sort of quantum keywords or buzzwords affiliated with them. So when we talk about a measurement, we first talk about a unitary U. This is equals 1 to n AI, and let's just U is unitary. So you can define the following maps. So we have U dagger. Let's see if I need to. Okay, if you guys understand this, this will be fine. QJ. These are maps from AJ to A. So when we defined byproducts, we had this notion of projections and also injections. So this Q is an inclusion. So I don't know if that, Walker, what notation did we use for that? Was it I or Q?
I actually used Jota, which I realize is actually not the time notation.
Yeah, no, I mean, that's fine. I'm making it clear now. So these are precisely those inclusions that we talked about there. And so a little bit of notation change won't hurt anybody. This is defined as psi dagger. And so we have some basic properties of how these Q's and P's work when you have byproducts. So this is PJ. This is a projection composed with U. And this is going to go from A to AJ. And so we have this commuting diagram. Psi j to A, QJ, equals 1 to N, AI, and something like this. So you can actually, why is this useful? We can actually define projection operators or the equivalent of projection operators from these. Yes? Okay, so we can define this PJ as being something like this, psi j pi j. Again, I'm using the notation from the book. Perhaps it would make more sense to just call this psi j dagger, but I'll just follow their convention. This is a map from A to A, which is exactly what we would want for a projector. And then, you know, it's not hard to show just based off of these definitions that you have PJ dagger equals PJ. You can also show that PI, PJ, something like this. And also that I equals 1 to N of PI equals the identity on A. Yes, that is not what they wrote, but that's probably what is
mean,
meant there.
It can
Yes.
also mean the product, but then it
No, I think it's the direct sum. That makes a lot of sense. Let me just check what they wrote. This is what they wrote, but yeah, I think that you're correct. Yeah, they just used the notation sum, but probably direct sum. From
From A to A, right?
yes,
Everything is from A.
yes, okay.
So you do a sum of those, get it out from sum of A.
Sum of A with itself on n times yes. Oh, hold on, but one second.
Oh, this is
Uh,
probably
yes,
I
yes.
think it would be good to specify what it is. Just, yeah, for operators, just a sum. But
Yeah, for operators, it's just the sum, and this is the notation that they use. Let's see here. What could they mean by this? More. It still goes from A to A. Yes, if it was the direct sum, then that would be something quite different. Okay, well, one thing that we can do, maybe will make it make more sense, is if we expand this. So, no, in the Hilbert space, it's more or less straightforward because these are operators or just matrices. You can add them. It's, you know, completely makes sense to put this sum here. So the
it is just the sum in the abelian group structure, or the abelian monoid structure. That's through the diagonal and then the codec.
Yeah, so you would go from A to direct sum of A's and apply the PI direct sum to go to direct sum on AIs and then go back to A.
mhm.
I mean, AIs are supposed to be A.
also, you go with the diagonal, then with this,
Yeah.
then with the projection.
Codec.
Yeah, the correct. Yeah, okay, diagonal, and that's supposed to.
Yeah, that's how we got the
Okay. Walk me through this for a second. What's the statement? So how should we write this? What's the better way to write this?
No, this is correct. I just forgot the notation I defined last time. No, the sum is just really the sum where you can add two morphisms of the same concept.
Sure. Yes.
And you do that by passing through
Oh.
first the diagonal that goes
Okay.
from A to a direct sum of A's.
Okay.
Then
Yes.
the direct sum of the PI's, and then
Uh huh.
My mistake is I treated that as a coproduct, but it's a byproduct. So okay, it's the sum in the concept.
Yes.
Yeah, but is it clear for everyone? Okay.
Okay. Yeah, I think it would be better to write.
The notation, but something like, I guess you go from A. Oh. There's this. Maybe it was denoted like this in Walker's talk. Then we have.
Ah. Okay. Yes.
And then I guess the co is denoted something like this.
Yes. Yes. That's right.
So so this is the sum. And
Okay.
we want this to be the identity.
Uh-huh. Okay. Very good. Yes, this is the notation that I missed out on. Okay. What was this from? No, I guess this was in Abramsky and Coecke as well. Okay, very good. Yeah, they probably defined it earlier. Uh-huh. Okay, very nice. And so we're just a couple of more things that are sort of unique to Abramsky and Coecke. They introduced some additional notions that are kind of more or less useful for quantum protocols, but maybe you wouldn't think to do this, or it's kind of not so interesting to do this just more generally in a category theoretic sense. So there's these notion of bases. So this is the notation of Abramsky and Coecke. So, oh, yes, actually, let's introduce this particular notation where they say n times x is defined as equals 1 to n of x. So we have that a base for an object A is a map from n I to A, which is supposed to be cherry. So I like to think of this in Hilbert space terms. We have, then we can maybe think of objects here as being c to the n. So base c to the n will be something like n times the unit object here in this category to Cn. This is like picking out some sort of computational basis. Okay, so now we can actually get back to the axioms of quantum mechanics. So let C be a, I will abbreviate dagger, or I'll write it, I won't be lazy. Then we have the following axioms of quantum mechanics. We want to say something about what the states are. We want to say something about how to prepare states. We want to say something about what the basic transformations are, unitary transformations, how we talk about measurements, how we talk about compound systems, these sort of basic constituents of quantum mechanics in this language. So we have a state space is an object A in C. So we have the notion of a basic variable. I mean, I'm following them here. This doesn't necessarily show up in any quantum mechanics textbooks as an axiom per se. Basic variables, and this will be something like base Q is a map from I plus I to Q. Q we can think of as some sort of state space for like a qubit. So this is like your constituent building blocks. Sure thing. Yes, it's an object in C. This is a particular object. I'm thinking here. I'm thinking here of the analogy with qubits, basically a two-state system. So you can.
Yeah, sure, but according to that definition, so is there any statement to perform like if there's a base with n copies of I guess it's unique,
Yes, there's a notion of dimension,
There are
yeah.
notions of dimension, they do correspond. It's not unique because you can twist it by homomorphisms, much in the same way bases.
I mean, the n.
Yes, yeah.
The n is
The n
unique.
is unique 'cause, I mean,
Yes.
ni and mi different n.
One way to look at it is you can define dimension just by being a trace.
Yeah.
And then from there, you can relate that in the case where you've chosen a basis to the sum of copies of one. So under some conditions on your scalars.
Then you can define a qubit to be like a two-dimensional state space with a particular choice of computation.
Yes.
Okay, good.
Very nice. So we also have this one will be as follows. So if I have two objects and I use the monoidal funker to map them to A, B, then I can also talk about, so this will be my composite or compound system. I can talk about having a base for A tensor B given by something like this. Base A tensor base B. And say that the dimension of this one was, say, M, and this is, say, N. So a base for AB can be given by a composition like this, where DMN is a map from NM dot I to, sorry, no, other way. NI tensor NI to NM dot I. Okay, so we don't need to really unpack that too much. Transformations. This one is fairly straightforward. It's exactly like you would expect. These are maps A to B, where U is unitary. So we also have the preparation of a state. This is going to be, so we have some morphism psi from I to A and a unitary U from I B to A such that we have the following diagram is going to commute. So we have an inclusion on the first, just by convention, we choose it to be the first element. So something like this. And we have psi, which brings us to A. And this has to commute. I guess this is the notation. So the idea, at least intuitively for me, is that you prepare a sort of, you single out a one-dimensional subspace, and you have a unitary that maps you into the object A. So, and then this has to commute. So I can define, this is a state psi, and I define the state precisely such that I single out a one-dimensional subspace and then apply a unitary. So I'm using the Hilbert space sort of intuition here. Is this okay? Okay. And let's see. Okay, so I won't have room here for this part. So actually, this will be 5b. So given some unitary spectral decomposition, this goes to I equals 1 to n ai. Let's define the following. Pi I equals 1 to n as a map from A to n A, where each of these n dot a's, these are each a copy of A, and these are going to be the different observational branches. Yes, I'm about to. Yeah, so where each pi, yes, is a map from A to A, is called A. So a couple of comments with respect to this one.
The PIs are also defined as before. You and the.
Yes, it's the same PI that I defined before. So just to be clear, this is, of course, a projective measurement, just following up on what Cihan said. So we're not talking about, just general POVMs, which, I mean, in general, I guess, maybe this later talks with the stuff with Selinger will include stuff like this. I'm not sure. One is that we sort of call the measurement is called non-generate if AI equals I for all I equals 1 to n. In this case, where if it is a non-degenerate measurement, then U is called U is called A. And I want to actually check the terminology here for a second. I wrote down destructive, but I'm not sure that that's correct. Destructive. It's called a destructive measurement. destructive measurement or observation. Okay, let's go back to here. So moreover, we had that, as was pointed out before, that we have psi I pi I. Defining this, pi I is called an observational branch.
Okay, but the terminology is a bit weird.
Yes, that's why I checked it. I don't actually. There's a technical definition of destructive measurements. I should probably double check this. This is their notation, but I will come back to this momentarily. Just gonna put a question mark here. I don't really see the connection here.
Do they have a name for the case where this doesn't hold?
No, they don't. Just yes, this was exactly. Anyway, I should have probably checked up on it beforehand. Okay, so 6a, I will call this branching for lack of a better term. So this is the following idea. So for F1 going from A to C, F2 from B to D, we want something like the following to hold. And this is what I discussed before. F1 plus F2 should be a map from A plus B to C plus D, which is just to say that you want to be able to employ sort of different morphisms on different branches. An example of this will show up in teleportation, where you actually want to apply a different unitary depending on which branch you're actually in. And so 6b is classical communication. We already discussed this in some sense. And that's the following idea, that we have that a tensor B plus C is isomorphic to a tensor B plus A. Again, this is called classical communication because in some sense, once you distribute this through, the tensor factor A actually has some sort of access to the result or the state that's actually in B here.
Okay, so the terminology there. So
I added this because everything else seemed to have a name except for this one, so yeah.
Basically, the term implies if we have like morphism from A,
Yeah.
the branching of it is an expression of it.
Yes. I think that if I followed what you're saying correctly, if I have two different observational branches coming from the fact that I had a measurement, I applied a measurement here, and so I'm getting A to n times A, where there's n copies because in principle I've applied n different operators here. So there's n different possible directions that this could go. And once I've applied such a measurement, I might want to actually apply a different morphism depending on which branch you're in. And so you have this sort of structure. Yeah. Okay, so have should I go over there? Okay. So the Born rule is a way for getting probabilities out of all of this structure. So let's consider a preparation I, comma, position U from A to I equals 1 to N AI with, geez, why the heck? Born rule. Oh, you know what? I think that this is a typo. This should be non-destructive. In fact, they say destructive in the note, but non-destructive is, I believe, what the correct terminology is here.
Oh no, yes, okay, but I don't think it has anything to do with destruction or non-destruction.
So sometimes people talk about destructive measurements in the sense that there's no post-measurement state or something. Yeah, I don't see that this is. So this is non-destructive in that sense.
In that sense, but it has nothing to do with the number of eyes components. Like
Yes, also not obvious to me. Yes. So the reason that I came back to it is because now I used non-destructive, and so okay. Yeah, I think it's a typo there.
What this non-degeneracy is saying in some sense is that your possible outcomes are each just basis states.
Yes, that's exactly right. Exactly. So now, okay, now it will be correct to say with non-destructive measurement. One of A and A, and we consider the following protocol, which is I psi to A to N dot A. And we're going to introduce the rule for computing probabilities. And that is the following rule. PR, and it will be given by psi dagger P I pi. Oh, sorry, no. And this is a map from I to I right here. So we just want to say a couple of things about this probability here. So I guess we can put this in a proposition. First, we have that PR PI psi. So first is that it's self-adjoint. PR PI psi. And second is that using this infamous sum here. We have that PR PI psi equals
Question. Here, you say preparation, but it seems like you just need a state, right? You don't need the decomposition I times plus B.
Well, I suppose what it really means is that this is a preparation, and actually, I believe I will use that fact later. Let me check. Do I? Yes, I use that fact later. Okay, and we have this one. Oddly enough, and I think that probably it's this structure is not strong enough for this piece. You don't get. Well, I suppose we know that PI is equal to. Sorry, I'm just sort of thinking on the fly. Do we know that these PRs are positive? I have to think about this. They don't claim it. There is a notion of a positive.
Positive scalar, right?
Yes. Yes, you can talk about a positive scalar, but I don't know that it follows immediately. Or maybe there is this positive morphism, which is defined as something like was like G dagger.
Yeah, I thought before. Yeah, I think because of the definition of PI,
Yes, I think it should follow. They don't say it, and I didn't check it, but it's something to follow up as an exercise to the audience. Show also that PR is non-negative. Okay. So for the first piece, we want to show, well, first, let's use the following. PI is equal to pi I dagger. Yes, okay, well, that's not incorrect. Anyway, PI psi is then going to be equal to, we have psi, this will just be some very basic algebra, psi, and I'm just going to use this same definition. I'm going to plug this in, pi I dagger psi. So when I look at this, I have psi dagger pi I and pi I dagger psi. In fact, I can just write this as follows. Pi I dagger psi dagger psi. So define some S I equal to pi I dagger psi, which is a scalar. Then we have that this is precisely Si dagger Si. And clearly, just from this, you can see that it will be self-adjoint. No?
I'm just trying to remember how you defined TIs before. There was the U, and then there were two structure maps.
The PIs?
Yes.
The PIs I defined as follows. PI is a map from A to A. And in fact, I had that, yes, I had that pi was equal to psi, yes, psi j, or sorry, I, pi I. This is just the dagger of psi. I guess it's also obvious. Oh no, okay. Never mind. Okay.
There was a diagram which takes A to A with U, and you had this. Sorry, it was direct sum of AI, right?
Yes. That was the spectral decomposition unitary. Was there a question about this? No, right? I think it's okay.
I was not sure if pi is equal to pi I composed with pi I dagger, because it was more like.
Yeah, I wrote it like this, but if you looked at the definition, pi I is just psi I dagger.
Oh, is it?
Yeah.
That's what
Yeah, it's.
It reverses the structure.
well, yeah, I can't remember all the definitions. Done in the measurement part. Yeah, that's what I was trying to remember. So you have the map from A to. Yeah, so that diagram takes you from A to direct sum of AIs. There's this U.
Yes, there's this U.
And you have these two maps which appear in the definition of PI, but I was not sure.
Yeah, the psi and. Yes, it's going to be something like this. If memory serves, I can write pi equals psi I pi I. Psi I is just a state, and pi I is defined as psi I. Yeah, I'm not sure what the point is of this notation, but it's
defined that way.
Yeah. Okay, for the second piece, we have the following that we're going to use. So start with the same pi I. Psi equals psi dagger.
Sorry, the other thing is the I's here, the AIs are I's here, right? So you have that case.
The AIs.
So A is
So,
equal to
come again?
from I over I, right?
Are you asking if this is a map over the direct sum or?
No, is this like a particular case where in the definition of measurements you have these AIs?
Okay, yes.
Everything is equal to I, right?
In the general definition of the measurement, everything is not necessarily equal to AI. Or sorry, equal to. In the non-destructive case, but if it's non-destructive, then yes.
Oh, okay.
Yeah. So I wasn't sure if you were asking about the general. Okay, so we want to use the following. We use that psi is equal to some unitary Q1 and also pi I. This strikes me as perhaps. Okay. So this is again talking about the fact that this is in fact a preparation. So we have this sort of unitary, so I should say this V is unitary U. Unitary. So then I'm just going to plug all of that stuff in here. It's just some basic algebra. Let's see. And also just recall that there's something kind of funky about this.
I mean, pi should be u of q.
Yes. That's what I was looking at. Let's go with that. Okay, let's see what happens for a second. So we're just going to rewrite this expression. Pi psi dagger is going to be VQ1 dagger, and we're going to use the fact that pi is equal to pi I and pi I dagger. So pi I dagger should be okay. Okay, anyway. U dagger. I think this is not correct anyway. P I. Sorry, this is not 1. This should be I. Q I. So U. Okay, no, it's okay. And psi here is VQ1. Okay, sorry about taking so long. So I'm just going to use the basic algebraic identities. Let's move through this fairly quickly. When I take this one, this will be pi 1 V dagger. No, not all the ones. Just this one is still 1. This is I. This is I for the ith observational branch. Yeah, I think that this is just convention that when they talk about a preparation here, this will just be you extract the first component, so to speak. I don't think that there's something very special about this.
Oh, you're decomposing it that way.
Yeah, exactly. Okay, so now we have U dagger PI, QI, U, V, Q1. Okay, so now we take we're going to sum over this I equals 1 to n of PR, PI, psi. Just so I don't bog you guys down in just algebra stuff, what you're going to see is nothing here depends on I except for these middle terms. When I sum over these middle terms, this is a projection, this is an injection. I'm going to get an identity here. Yes. An identity on, I guess, AI, or I in this case. Exactly. So I'm going to get identity on the unit object, and then I'm going to have, after that, these U's are going to cancel, going to give me identity. Then the B's will cancel, and then you have that P1 and Q1. This one will also give identity. So just to save you guys the details, this one ends up being identity. Yeah, I know, but it just doesn't make sense to go through all of those steps right now, unless you guys find that it would be very, very useful. Is it okay, or? Okay. Okay, so I'm going to return to this, our sort of running example of the seminar, which has been this example of teleportation. And let's see if we will have enough time. So just as a reminder, because we sort of want to bring things a little bit full circle, we had that there was this picture in the circuit diagrams of something like so the outcome of this measurement in the Bell basis, I will use dotted lines to denote a classical channel, just because my double lines look very ugly. No other reason than that. And we have that this is some Bell state, B0, 0. Now, there was also this other notion, which I'll just put in a different color, or rather, just to something squiggly. It's more or less the same picture. And this one was, okay, I'll do it like this. So we have some U here, U here. And so we had, in fact, a string diagram picture that looked like this. So actually, now we're going to do this again a little bit more formally, just to show how this thing actually, in fact, works. In fact, you can show that the end result of a diagram like this, oh, sorry, there should probably be a U dagger here somewhere, that this thing is just a straight line.
Wait, how does the first one work compared to the second?
How does the first one? Ah, okay, very good. So if you look at the first one, you have two basic properties. You have the preparation of this Bell state, and then also this measurement here. Okay, so the preparation is going to be, if I'm not mistaken, this part of it. One second. No. Bottom to top. Yes. Yes. So this is our preparation here of a Bell state, and this is the independent first party. And then you have this Bell measurement here, more or less. Yes.
So UXY is U, right? Or
I mean, more or less. So we're going to actually show that this diagram works by actually just looking at the categorical diagram. Yeah.
So I think that the first U is part of the Bell
yes, that's in fact the case. Yes, the UX, so the U is part of this, and more or less the different observational branches will be me applying a different U to each of them. So in fact, yes, this U can be part of this coname. I think that this is just how they drew it in, sorry, Vickery Hoynen. So, okay, hopefully we have time for this. I'm going to draw the same sort of big commuting diagram that I drew in the second seminar of the sequence, and hopefully just go into it with a bit more detail. In fact, I wonder if maybe that's a better way to do this. Okay, let's do it like that. And so I'm going to have 3 different Qs here. Let's think about this for a second. QA, QB, C, B objects in our category. And we think of these as being identical objects. So we have some map, say IDAB is a map from QA to QB. And similarly for AC and BC and so on and so forth. So we think of these as identical objects. And so there are some additional sort of maps that we should define, but what I'm going to first do is just draw this big commuting diagram and then sort of fill in the details.
Really want them to be I mean, I don't know, it feels natural to say we choose an
Yeah, that's fine. But at the same time, we are identifying bases in each.
Oh,
So yeah, in principle, I guess, yeah, you're right. So, see if I can, I'm not as tall as Walker. Let's see, maybe I should go side to side. So, QA, QA, and we will go, okay. So these are obviously the same. And all the way down here, let's see, however long I need to draw this, there will be something at the other end, which is going to be 4 times QC. Now, where's the 4 times QC coming from? We are going to do a measurement here. And when we measure here, we're going to get 4 possible outcomes. So there's going to be 4 copies of the final state QC, or the final object QC. And each of the 4 different branches, well, actually, what we want is that each of the 4 branches, no matter what, if we apply the correct unitary, will always give us psi on each of them. But the point is also just that we have 4 branches on the 3rd qubit QC. So that's where this is coming from. Just make this bigger. So we have the following row A, so that this thing is going to be QA tensor I. Okay, this is okay. Then we have the preparation step. This is the part where we prepare the Bell state, this one right here. So we apply here IDA tensored with IDBC, the name of this. And this one will give us QA tensored with QB dual tensor QC. This part maybe I will require a little bit of elaboration, but the point is that we can always define the name of a morphism. In this case, the morphism is just the identity. So this is just us using, I guess this is the unit. Let me think for a second. It's not quite the unit. This is the same mistake I made last time. Okay. So if I use eta on QC, then this will be, okay. QC star tensor QC, okay. And then we have precisely identity on which one do I want to do this? This guy. So it will be something like identity B. There's a star that needs to be there, yeah. Yeah. And identity C. And then, so we have Q, B star, tensor, QC. So we have this guy right here, which is identity BC, like this. So we want to rearrange things here. This is going to be, so we can use from symmetric monoidal categories, just like the general structure, we have something like A, B, C, so that we can rearrange this to be QA tensor QB star tensor QC. This is okay. And then, so this part will require a little bit of elaboration. So here we have this observation step. So it will be, and I will fill this in momentarily. For I tensor QC. So there will be some map here, which is going to be like a measurement that I will call S dagger beta I equals 1, 2, 4.
So the ADC, which wires do they correspond to?
So A and B are going to be the very first two, like this. So what are we doing here? This is precisely the step where we get an observation, 4 times I out of each of the, after performing a measurement on this part. So we also want to, and I will still not have enough room probably, so we'll see how this works. Here, what we want to do is precisely this right distributivity. So this is the classical communication step. I will call this VC. What is VC doing? It's just distributing this direct sum here. So you have 4 times I tensor QC. Now, then we can also use the fact that each of these should be natural isomorphism to QC. So I will write this as 4 times lambda C inverse, where lambda C inverse, basically, what does that do? It takes I tensor QC to QC. So then we just have 4 QC. And now there's an additional step that I need to talk about, but the idea is that in addition to this, I have these following maps plus I equals 1 to 4 of beta I C inverse. Okay, where is this coming from? These betas are going to be unitary morphisms, and these are going to be precisely those ones that are the corrections. So what is this? This is me applying to each of the different branches one of the different corrections.
Aren't they just UXI? Or XY?
Yes.
Okay, well, you're calling them beta, just the same thing.
Yeah. I'm following the convention of Abramsky, and yeah. No, it's precisely the UXYs. Well, the one on each different tensor, or the one on each component is a UXI, XY. Okay, so I have this. Okay, so let me just move this around a little so it looks nicer. I equals 1 to 4 beta I C inverse. Is that okay? And then, yeah. Okay, and so there's this map that they call delta AC4, and this whole thing, I mean, it's claimed that it commutes. So what is the part that I need to talk about here? This is the 4QC. This is the part where you're correcting everything. This map right here basically is more or less, so if you guys will indulge me for a second, this delta AC4. Yes, exactly. Because you want it to be the same, psi for every single, that's exactly what it is. So the risk of, so I don't know if this will be useful. There's some scalar here. We put some properties on this scalar. I equals 1 to 4, and this is a map from QA to 4 times QC. And it's precisely as Reddy just said, you want this thing to be the diagonal. So it's a weighted diagonal, actually. You have to worry about these scalar pieces coming out. So I didn't go too much into that, but more or less, this is just a weighted diagonal so that you're getting more or less the same state on every component, which is exactly what we expect.
In building this diagram, it seems like the only sort of, at least to me, the only non-trivial part is where you do the corrections there. Because I mean, you do QA times I. All of these are like the canonical structure.
Yeah, like
There's
that's
happening there.
yeah, I agree with you. So here, that I actually wanted to impress on that. Yeah, so here, this is part of the basic structure. This also more or less, this also, this piece requires a little bit of digging into, actually, because it also has the daggers and scalars and stuff coming in. This is probably the non-trivial step.
Yeah, okay. So that's where you get.
Yes.
In the string diagram.
Yeah, okay. So that.
Exactly.
If you take off the indexing, so take out the 4s, so i's, then it's a lot. Then it really does collapse to the I as you.
Yeah, so that part is not clear to me. How do you get the diagram without any indexing of the U?
Okay,
Or is
so
there
Ye-
anything external that you have?
no, what I'm saying is fix one of your BIs to be
Yeah.
Beta, the betas.
Okay, beta.
Yeah, yeah.
um, so
So if you,
now, what you're doing is at this step you're choosing one branch.
yes,
Like, not saying, oh, there's some probability of getting 4 branches. So you get rid of your indices, chosen your beta J. Then what you're doing is you're plugging in a unitary there after taking the unit. And then you take the co-unit. No, after yes, after plugging in, you take the co-unit and the unitary, and the delta goes away because you're sticking just yet.
so I think that what Walker is trying to say is that this is only talking about a single branch. Yes.
That must be interesting.
Yes.
Yeah,
Yeah.
it's one of your main mechanics.
Okay, I think that that's more or less what I plan to say.